Thank you. All right, so I'm going to get rolling here because this lecture is a challenge for me to finish in 50 minutes. So once again, you got your learning objectives there. You guys can use those as you see fit. So we just talked about nucleic acid structures, including the structure of DNA, and now we're going to talk about DNA replication. Structure, actually, logically, the next logical step is to talk about DNA replication. The structure kind of actually suggested originally how it does get replicated. So a couple terms. DNA replication is bidirectional and semi-conservative. This should say bidirectional. I let somebody borrow my PowerPoint and they messed a couple things up on it. And I didn't catch that. But it should say bidirectional right there, not birectional. I don't know what that means. Sounds very provocative, doesn't it? But so what that means, bidirectional, in terms of DNA replication. So I'm going to use a number of terms here that may have different definitions outside of molecular biology, but I'm talking about the molecular biology definition. Bidirectional, so DNA, the replication is going to begin somewhere in the interior. So we have an example here of a circular chromosome and a linear chromosome. Okay, circular would be bacteria, linear would be eukaryotic nuclear DNA. It's going to begin somewhere inside, okay, and then it's going to go in both directions. Okay, so you can see right here we opened up the DNA and it's going in both directions around the circle. Or in case of the linear DNA, we opened up the DNA and we're going in both directions. Okay, that's what we mean by bidirectional. It's going to go in both directions when we replicate the DNA. We have this next term, semi-conservative. That means each copy of the DNA molecule after a replication contains one of the original strands. So we have a DNA strand we're going to replicate, okay, and we're going to separate it, and we're going to copy it. Well, when you're done, you end up with two DNA molecules. If you look at those two DNA molecules, individually, each one will have an original strand from what we started with and a newly synthesized strand. Of course, there'll be the opposite in each one, but each one will contain a newly synthesized strand and one of the originals. That's what semi-conservative means, okay? Conservative would mean that we actually replicated the DNA and then somehow separated them and put the two new strands together and put the old strands back together. But we don't do that. But that's what semi-conservative means. In prokaryotes, we actually have one origin of replication. Okay, that's sufficient to replicate a prokaryotic chromosome. Whereas in eukaryotes, we have multiple origins of replication. These aren't exactly drawn to scale, obviously, but eukaryotic chromosomes tend to be enormous compared to a prokaryotic chromosome. Prokaryotic chromosomes don't have very much extra DNA in there. Eukaryotes, 98% of the DNA is junk. Okay, it actually does have a function, and we're learning more and more about some of these functions, but it's not encoding proteins. Okay, so that means that the chromosomes are absolutely enormous. In order to replicate it in a reasonable amount of time, we actually have to have multiple origins of replication. Okay, so what we're going to do is we're going to look at a model for prokaryotic DNA replication. The reason we look at prokaryotes, it's much more well understood. Still working out some of the details for eukaryotes, still working out some of the enzymes. Okay, they're getting closer and closer, but the prokaryotic model has been known for a long time. It's really well established. So we look at the prokaryotic model. If you understand it, you understand all the things that have to happen to replicate eukaryotic DNA, with one exception, which we'll talk about at the end. So the first thing we're actually going to have to do to replicate DNA is separate the complementary DNA strands. Okay, that means these origins of replication that we talked about need to be melted. Okay, so if you remember in the last lecture when I talked to you about melting DNA and hydrogen bonds, which DNA or what is the composition of DNA that's the easiest to melt? Yeah, where we have AT base pairs, it's much easier to melt. So you'll see the origins of replication in DNA tend to be very AT rich. Okay, that allows us to separate and make this first replication bubble. In prokaryotes, this is accomplished by a protein called DNA A protein. Now, once you've opened up a bubble, separating, it's kind of like a zipper moving along. It's much easier to separate a single nucleotide base pair at a time. So then it doesn't matter what the composition is. But to open up that bigger bubble at first, you need the AT base pairs. So you'll see that there. You'll also see this in transcription as well. We'll see the same theme in transcription. So that's the first thing we got to do, melt that origin of replication. We have our DNA A protein. Now we need to form the replication fork. First thing we got is we have these proteins called single-stranded binding proteins, or SSBs. Very frequently they just use the abbreviation. This binds to the single strands and keeps them from immediately reannealing back on each other, and also provides a level of protection. So DNA, when it's naked, is more exposed to nucleases, and when it's single-stranded, is even more exposed to nucleases. Okay, so that's where it's at its most vulnerable point. So SSBs also are going to protect that DNA. Then we have this enzyme called a DNA helicase. So what this helicase does, and right here it looks like this triangle wedge, it's actually going to move along the replication fork in this direction, okay, in that direction, trying to actually separate the DNA, okay? So it's peeling apart that DNA. Once that replication bubble is opened up, DNA helicase can move along and peel apart the whole rest of the DNA, base pairs at a time. And once again, as it moves along, the SSBs come along and will bind to the DNA and keep it separated until it's able to be replicated. Now, DNA is a helix, right? We looked at the structure in the last lecture. So what ends up happening is if you take a helix and you separate the strands of DNA, okay, and you can demonstrate this for yourself if you want. You can take your shoelaces and make a helix. If you start peeling apart the shoelaces, what happens is you're going to create supercoils. What's supercoils? We already talked a little bit about supercoils when we wanted to create supercoils, when we wanted to condense our chromosome, or when bacteria wanted to condense their chromosome, right? But when we're trying to replicate DNA, supercoils become an issue. They become a problem. Okay, so as that helicase moves along and it's separating these two strands, the DNA in front of it starts winding back on itself and creating these supercoils. If you don't do anything about it, eventually the helicase will get stuck and it won't be able to move. Those supercoils will become so tight, it won't be able to move any further. So we have to do something about those supercoils. And in order to do that, we have these enzymes called topoisomerases. Their job is to alleviate the supercoiling. You have some topoisomerases that also can introduce supercoiling. And actually, sometimes they alleviate supercoiling by introducing the opposite type of supercoiling. But anyway, what I want you to think about when you hear topoisomerase is supercoiling. Just associate topoisomerase supercoiling in one way or another. Okay? Either creating or removing supercoiling. But that's their job, to deal with supercoiling. You have two types of topoisomerases, type 1 and type 2. Type 1 just cleaves one of the two DNA strands. So when you have this wound up DNA and you clip one of the strands, what it does is it gives it a way for the DNA to spin around, and it'll actually all unwind and spin around that one strand. Okay, and then when it's done unwinding, then you religate that single strand back. So that's one way you can relieve supercoiling. Get this twisted up DNA, snip one of the strands, it'll unwind itself, and then actually religate it. That's a type 1 topoisomerase. The type 2 topoisomerases actually will cut both strands. Obviously, when you cut both strands, it's very easy to visualize. You can just unwrap and actually religate back on itself. So they have two enzymatic activities. They have the ability to religate the DNA, and they also have the ability to cut the DNA. Okay? So, and once again, we saw this in the last lecture, but there is a special type 2 topoisomerase called DNA gyrase. Its job is to actually introduce supercoils in bacteria to actually condense their chromosome. And actually type 2 topoisomerase actually will, the DNA gyrase will actually separate the two strands. So DNA gyrase is a special one of the type 2 topoisomerases. All right. Okay, so we have the direction of DNA replication. So all polymerases that synthesize nucleic acids. Okay, this is where we don't have a virus exception. This is an absolute rule in molecular biology. All polymerases, RNA polymerases, DNA polymerases, doesn't matter. All of them can only synthesize nucleic acids in the 5' to 3' direction. That's an absolute rule. Only do 5' to 3'. Since the DNA molecule is actually anti-parallel, right? We already talked about that. One strand is going 5' to 3', the other one's going in this direction, 5' to 3'. That means if we synthesize 5' to 3', we must be reading the template 3' to 5'. And that's what's going on in all these figures as we move through the rest of this PowerPoint. So once again, synthesize 5' to 3'. That means all these polymerases are going to read the template. RNA polymerase, DNA polymerase, doesn't matter. They're going to read the template 3' to 5', synthesize 5' to 3' to create the anti-parallel molecule. So at each replication fork, one strand of the DNA can be replicated continuously. So as we move from left to right in this figure, you can see if we look at so this is a bubble in there, and it's going to be going in both directions. But if we separate it in half and just look at this black strand on the top, that's a leading strand. And as we're moving along, and the helicase moves along and opens it up, we can just keep making that strand. The problem is, immediately below that, we're also replicating that strand, but in order to do it correctly, in order to synthesize 5' to 3', we actually have to go away from the replication fork. So that creates an issue that we need to solve. So how can that happen? So it's easy to see how the leading strand is going to be synthesized. Just keep opening up the DNA and it just keeps moving along. But the others have to go in the opposite direction. So we actually synthesize one of the strands discontinuously. That means what we'll do is we'll open up a stretch of DNA. Doesn't matter how big it is. Let's say it's 100 nucleotides. And then we'll replicate that DNA going away from the replication fork. Then we'll open up another section. We'll go away. Okay? And on the opposite strand, we're actually going towards the whole time. Okay? So these smaller fragments are called Okazaki fragments or lagging strands. Okay? You'll see both of those terms used. They both mean the same thing. The Okazaki fragment was named after the person who discovered it. Now later on, we can take all these short segments and we'll actually join them together as we're actually going to see. Okay, so one thing that differentiates DNA polymerases from RNA polymerases is DNA polymerases require a free 3' hydroxyl group to begin synthesis. This means there has to already be something there to join onto. If you remember in the structure of DNA or RNA, at the 3' terminal end, you had a free hydroxyl group. That's where you're going to add on the next nucleotide. And DNA polymerases can only add on to something that's already there. That's a property of DNA polymerases. So that creates a problem when we open up a replication bubble, right? We have some DNA polymerases that are going to synthesize DNA, but when you open up the bubble, there's nothing there to start from. So the first thing you have to do is lay down a primer, which is done by primase. Primase is actually an RNA polymerase. RNA polymerases can actually begin de novo. They don't have to have a free 3' hydroxyl group. They can take a single-stranded nucleic acid and just start synthesizing, just start copying. So DNA synthesis for each one of the strands, each leading strand and each lagging strand, begins with this primase. Primase comes in and lays down a short molecule of RNA, say 10 nucleotides or so, something like that. Okay? Once that's down, then the DNA polymerases can come in and continue synthesis from there. Okay? But obviously, at some point, we're going to have to get rid of that RNA. And I'll show you how we do that later. So once again, both the leading and each one of the lagging strands begins with an RNA primer. It's kind of shown in blue in this figure. So now we're actually showing you only one side of that replication fork. Our helicase coming in there, separating. We got our topoisomerases out here, leaving the supercoiling. Okay, we got our RNA primer being laid down by primase right here. And for each one of the lagging strands, you got to lay an RNA primer down. Okay, that's where we are so far. So now our DNA polymerases can come in, and they're going to catalyze the reaction between the 3' hydroxyl group, the end of one of the strands, and the 5' triphosphate of the incoming nucleotide. Okay, which nucleotide is going to come in? Well, that's going to be defined by the template strand that we're actually reading. Okay, so this is a growing chain. It's being synthesized, 5', 3'. That means we're reading the template, 3', 5', and we're synthesizing in this direction. Next nucleotide is a C. What base pairs with that? G. So we'll have, in this case, we're making a DNA molecule with deoxy-GTP. Okay, come in. And actually, this synthesis of DNA requires a lot of energy. The energy, in this case, actually comes from those acid anhydride bonds in the nucleotide itself. Okay, so in the net reaction, we're actually going to add this next nucleotide, and we're actually going to cleave off this pyrophosphate, which is shown right here. That's those 2 phosphate groups at the end. What's not shown in this figure is we're actually going to cleave this pyrophosphate into 2 inorganic phosphates. What that does is it actually serves to drive the reaction forward, because if you accumulate a whole bunch of pyrophosphate, eventually it'll, because of the way enzymes work, it'll actually start inhibiting the enzyme. So you drive it forward by cleaving that. The reason I mention that is because you see that you're going to see this same theme over and over and over and over again in biochemistry, where you have this second reaction where you cleave off the pyrophosphate to drive a reaction forward. Very, very common. Coupled irreversible reaction. And so what that means is for every nucleotide we add, we actually cleaved 2 high energy bonds. That means DNA and RNA synthesis require a great deal of energy. Very energy required. Now, the enzyme that actually does the bulk of the work in prokaryotes, once again, we're still talking about prokaryotes here, is DNA polymerase III. DNA polymerase III in prokaryotes is the workhorse. Okay, it's going to do the bulk of the synthesis of the DNA. It extends both the leading and the lagging strands. Okay, once the primase lays down the primer, DNA polymerase III is going to come and copy the rest of the DNA. Okay, but we're not done yet. Okay, so as the DNA is being replicated, it needs to be as accurate as possible. I've already shown you, for example, we talked about sickle cell anemia. Sickle cell anemia is a single nucleotide base change. And there's some diseases much more severe than sickle cell anemia where you have a single nucleotide that's been changed. Okay? So DNA replication needs to be as accurate as possible. We can't afford to accumulate mutations. And you've got 3 billion base pairs in your genome. So that's a lot of nucleotides to copy accurately. And polymerases absolutely do make mistakes. Okay, a polymerase that doesn't check its work, which we're going to talk about right here, every, on the order of in the thousands, it'll make a mistake, okay? So if you're talking about a genome that's billions of base pairs big, and you didn't have some kind of way of fixing the mistakes, you wouldn't be able to survive, because it would accumulate so many mutations every time it replicated that it would be crazy. And that's partially how viruses mutate so rapidly, because they don't often proofread their work. Okay, and they work a little differently because they just work by numbers. They just have billions of copies. Okay, but that doesn't work for you guys. Okay, so but we're still talking about the prokaryotic model here. But we're going to have the same thing in eukaryotes. So polymerase III has proofreading activity. What that means is it checks every nucleotide it adds as it's going along. Okay, so every time it adds a nucleotide and it moves on to copy the next one, it checks the one it just added. Okay, if it incorrectly base paired, okay, and it can tell if it's incorrectly base paired, it will actually move backwards and cleave the nucleotide it just added, and then once again move forward with its polymerase activity. So this is an additional enzymatic activity associated with many DNA polymerases. It's a 3' to 5' exonuclease. So DNA polymerase III has a 5' to 3' polymerase activity, and all DNA polymerases and RNA polymerases have that. But it's also got this proofreading activity. So I want you to also realize 3' to 5' exonuclease activity is proofreading activity. Okay, you can use these interchangeably in this case. Okay, so once again, DNA polymerase III, it's moving along, it's copying everything, it checks its work as it moves on to the next nucleotide. Anytime it sees that it made a mistake, it shifts backwards, cleaves that nucleotide out, and then hopefully corrects the mistake. So it keeps moving along. Every time it encounters one, it will try to correct it. Now, occasionally they still make mistakes, and we're going to deal with how we fix that later on. Okay, so in order to complete the replication of this DNA molecule, we're going to have to, and we're still talking about circular DNA here because we're talking about prokaryotes. We're going to have to join the Okazaki fragments, join those leading and lagging strands. We're going to have to take care of. So at this point, what we're left with is we've got various pieces of DNA that have been copied, and we have RNA primers in there, and we have all these little nicks too. So what we have to do is we have to come in, remove the RNA primer, replace it with DNA, and then seal up all the nicks. Those are the final activities we have to do. In prokaryotes, most of that work is accomplished by DNA polymerase I, okay? Just like DNA polymerase III, it's got a 5' to 3' polymerase activity, okay? So it can work just like DNA polymerase III. As long as it's got a free 3' hydroxyl group to join to, it can make a molecule of DNA, see? So in here, where there is a RNA primer gap, RNA primer, that we're going to actually remove that RNA primer, but it can actually join. In this instance, there'd be a hydroxyl group right there. It can join that and then move on till it gets to the next DNA molecule. As it's doing that, though, it's actually got an additional activity. Okay, it's got a 3' to 5' exonuclease activity. What did I just tell you that was? That's proofreading, right? So it does proofread, just like DNA polymerase III. It does proofread, but it's also got this additional activity, this 5' to 3' exonuclease. So this is an exonuclease when it's moving forward. And DNA polymerase III does not have that. And what that activity is for is to remove the RNA primer. So what you'll see is it comes in, you have, in this case, we have some lagging strands. We have an RNA primer there. What it'll do is it'll come in, it'll have a 3' hydroxyl group to add on to, and it'll start polymerizing DNA. And as it moves forward, polymerizing that DNA and checking its work, it's got proofreading activity, it's removing the RNA primers in front of it. Okay? So it comes in and basically patches up all the places where those RNA primers are. It patches it up with DNA. And it does that by its 5' to 3' polymerase activity, also proofreads with its 3' to 5' exonuclease activity, and it removes the RNA primers with its 5' to 3' exonuclease activity. So you'll have to spend a little bit of time getting those things straight in your head and know, the polymerase is pretty straightforward, but the exonuclease, just remember, 5' to 3' exonuclease is to remove RNA primers. 3' to 5' is for proofreading activity. So this 5' to 3' exonuclease is actually removing correctly base paired nucleotides, right? The RNA primer presumably was synthesized correctly. It's correctly base paired, but it's RNA, and we're trying to get rid of it. Ultimately, you don't want to leave RNA in the final DNA molecule because RNA molecules are much more labeled. And so that means they're subject to degradation. You want to keep your hard copy as intact as possible. This 5' to 3' exonuclease activity, which can remove correctly base paired nucleotides, is going to be important for another Pol-1 function, which is going to be, it also, Pol-1 has an additional role in DNA repair, as we're going to see later on. So finally, what we're left with now, we've actually replaced the RNA primers, which you've got a double-stranded DNA molecule now, and all you're left with is a few little nicks. So everywhere where that DNA polymerase came up, removed the RNA primer, there's still going to be a little nick there, and so we have DNA ligase, which comes up and seals up and creates those last phosphodiester bonds that complete the joining of the molecule. Okay? And really, that's all there is to prokaryotic DNA replication. Now, in eukaryotes, they're still working out some of the details of what's going on, and this is as much as I'm going to tell you about eukaryotic DNA replication. First thing people are going to do, they're going to be like, okay, Dr. Lucia gave us these enzymes. Okay, I know DNA polymerase 3 does most of the work. Where is it in eukaryotes? Or DNA polymerase 1 comes in and does this. Eukaryotes have different enzymes. They all have to, ultimately it has to do all the same enzymatic activities, but it doesn't work exactly the same as in prokaryotes. For example, this polymerase alpha actually, strangely enough, has a primase activity in it. So it doesn't have a separate primase. So this is a weird enzyme because it's an enzyme that's an example of something that's both a DNA and an RNA polymerase. Maybe to you guys that doesn't stick out as being weird. To me, that's very weird. You don't normally see that. Okay? And so the primers that it actually lays down are RNA-DNA hybrids, which is very, very odd. You also have different enzymes that elongate the leading and the lagging strands, or at least that's our current model. That doesn't happen in prokaryotes. Prokaryotes, polymerase 3 just comes in and does both, does all the bulk of the work. In eukaryotes, you have a separate one that does the lagging and the leading strands. Why? I'm not sure why that is. But these 5 enzymes, alpha, delta, epsilon, beta, and gamma, are the 5 that you may run across in your reading somewhere. Pol beta is a DNA repair enzyme, so it has some polymerase 1 in prokaryotes is a repair enzyme, but also it happens to have functions during normal DNA replication, as you just saw. So in eukaryotes, they have more enzymes, and in most cases, the enzymatic activities are separated a little more. And once again, they're still working on these models. So, however, one thing that you do have to deal with in eukaryotes that you don't have an issue with in prokaryotes. So in prokaryotes, with a circular piece of DNA, what I showed you is enough to replicate the entire DNA molecule. There's no other enzymatic activity required. Everything that I showed you will is all that's required to replicate that molecule. However, when you have a linear DNA molecule and all of your chromosomes are linear, okay, you end up with an issue, okay? So when you get to the end of the DNA molecule here, where's my pointer? You get to the end of the DNA molecule here, and you remove that RNA primer, okay, you've got to lay down an RNA primer, synthesize some DNA. At some point, you're going to have an RNA primer you're going to remove, and you're going to want to synthesize DNA, but there's nothing to add on to when you get to the end. So the ends of eukaryotic chromosomes always have a single-stranded piece of DNA hanging over. Okay? Where this becomes a problem is, over time, if you keep replicating that piece of DNA, okay, and you don't do anything about the end, what happens is over multiple cycles, that end is going to get shorter and shorter and shorter and shorter, till eventually it gets to the point where it gets into some coding genes. And if that happens, that cell will undergo apoptosis and die. Okay? So obviously they have to have a way of dealing with the end of the DNA. So the ends of eukaryotic chromosomes are called telomeres. Okay? And you have an enzyme called telomerase. And what telomerase is going to do is it's going to extend the ends of that DNA molecule out so that when it's replicated, it doesn't keep getting shorter and shorter and shorter until you come to a critical point where it can no longer get shorter without interfering with genes. So in eukaryotes, you have a 6-nucleotide repeat, okay, that just repeats over and over and over again. That is the telomeric region, and it can repeat over 1,000 times. So how is that actually? So what we've seen so far, the enzymatic activities that we've seen so far can't accomplish this activity. So we have something additional that we're going to do here, and this is with an enzyme called telomerase. Telomerase's job is to extend the end of telomeres. Okay? So the telomerase itself is actually, and that's what's shown in orange. In the green or yellow, it depends on how, I guess, how well you see. I don't know if that's green or yellow. Kind of like pea soup there. That's an RNA molecule. It's actually part of the telomerase itself. So telomerase has both an RNA component and proteins. Okay, so the orange part's supposed to be the proteins. So that RNA part of the telomerase is actually has a complementary region to that 6-nucleotide end. Okay, so it's going to bind to the very end of the DNA. And the region in front of it actually serves as a template. Okay, so now this, the telomerase itself has a DNA polymerase activity and can actually extend this single strand out. So what it's going to do is about 6 nucleotides at a time, it's going to add 6 nucleotides here. Okay, and it's going to shift down, add 6 nucleotides. And that 6 nucleotides it added is now complementary to this section over here. So it just keeps moving down, add another 6, move down, add another 6. So what you've done is you've just extended this end of the chromosome way out. Now you can come in, add a primase, or the primase activity can come in, lay down a primer, and extend it back. Okay? And so that will actually extend the end of the chromosome. So first of all, that makes telomerase a very unique enzyme because the template that it's copying is part of the molecule itself. It doesn't need the DNA molecule to provide a template. All it needs is a complementary place where it can bind. It actually has the template. It's weird because the template is actually an RNA molecule. This green thing right there is an RNA molecule. It's copying that RNA into DNA. This is an example of a reverse transcriptase. It actually violates that central dogma that I showed you before, where we go from DNA to RNA to protein. Here we're going backwards. Copying an RNA template and making DNA. Okay? So this is an example of a telomerase, or I'm sorry, of a reverse transcriptase. Reverse transcriptases are very, very common in viruses. Okay, but this is one example, a natural one that's in your cell. HIV is a good example of an enzyme which has reverse transcriptase. So this process is going to be repeated many times. You can extend that way out. RNA, the primase activity in eukaryotes will come in, lay a primer down. You can synthesize some DNA. You're also going to come in later and remove that RNA primer. So one thing that does happen in eukaryotes is you always have a little piece of single-stranded DNA left at the end. Okay? So that's where that RNA primer was. It's always going to be left. Eventually, you can't fill that in because you can't synthesize 3' to 5'. So you can't backfill it in, and there's nothing to join onto. So there's always going to be a little piece of single-stranded DNA at the end. And that piece of DNA, I told you single-stranded DNA is much more vulnerable to nucleases. It actually will fold back and create a special structure. You actually get a triple helix at the very end of the DNA, but that will help protect it. And there's also some proteins there. So a few things about telomerase, though. Telomerase is not present in all cells, right? So it's only going to be expressed in cells that continually divide and are not terminally differentiated. So stem cells will have telomerase activity. Once a cell becomes terminally differentiated, once a cell becomes a hepatocyte or a liver cell, for example, it's not going to go backwards. Okay? At that point, you shut, at least under normal circumstances, it's not going to go backwards. In that case, telomerase gets shut off. So what ends up happening? That cell line now, from that point on, has a finite number of divisions. Okay? And at some point, it's going to divide, and it's somewhere in the neighborhood of 30 to 40 cell divisions, typically, before the telomeres, which are going to get shorter and shorter on every round of replication, will get short enough where it's going to interfere with the genes, and that cell will actually undergo apoptosis or apoptosis, however you want to pronounce it, okay? Which is programmed cell death, if you haven't seen that yet. However, you can, in certain instances, activate telomerase, and in many cases of cancer, this is what happens. If you look at cancers, about 90% of cancers, now if you're not familiar with cancer, haven't been introduced yet, basically you can think of cancer as uncontrolled cell division. Okay, well, uncontrolled cell division will eventually limit itself if no telomerase is there, right? It'll only divide a certain number of times, and so it'll be self-limited. So cancers have to figure out a way to deal with the shortening of the telomeres, and about 90% of the time they actually do that by activating telomerase. So, and sometimes it plays a very critical role in the induction of cancer. Once again, I already told you that telomerase is an example of a reverse transcriptase going from RNA and DNA, violating our central dogma. You see this in many viruses. A lot of viruses have telomerase. I'm not sorry, telomerase. Reverse transcriptase activity. Telomerase and reverse transcriptases don't have proofreading activity, so they're subject to mutations. In the telomeres, it's not a big deal if you have a mutation. It's not encoding a gene, so it's not that big of a deal. Okay, so the next thing we're going to talk about now is DNA repair. So as we went through and we looked at the replication of DNA, I told you you had that proofreading activity, right? However, the proofreading activity doesn't catch every mistake. It does a pretty good job, but you still get mistakes in there. So after DNA replication, there's going to be a process by which the DNA is checked to make sure there's no mistakes. Actually, there's always mistakes, so I should say it's checked where the mistakes are so we can actually come in and fix it. So this is what's known as strand-directed mismatch repair. Okay, this is one example of DNA repair. And this is going to be distinct from another example of DNA repair that we're going to talk about. So strand-directed mismatch repair is specifically going to correct errors made during replication. Okay, so why is it strand directed? Let's think about that for a second. Well, I told you before, you end up with a newly synthesized strand and an old strand, right? And when you replicate DNA, well, only one of those is technically should be correct, right? If there's a mutation in there, if there's a change in there, how do we know which one is actually the mistake and which one's actually correct? Well, that's how we have strand directed. So the template strand and the newly synthesized strand are distinct. And I don't think I've written in here how they do that, but they do that through methylation. So the old strand is going to be methylated, the new one won't be, so they know the old strand should be correct, right? So anything, the new strand is where a mistake could be made, and that's what we mean by strand directed. So we're going to correct the newly synthesized strand. So certain proteins, and we're not even going to mention any specific ones, but there's a bunch of them, are going to come in and check the fidelity in this case. Check to see if there's any mistakes. When it moves along and it finds a mistake, it knows which strand is the newly synthesized strand. There's going to be some enzymes with endonuclease activity. So I've used the term exonuclease already. Let me explain what I mean by endo and exonuclease, because I'm going to use these again. Exonuclease always acts on the very end of a molecule, either the 5' end or the 3' end, but it's always acting on the end of a molecule. Endonuclease cleaves somewhere in the middle. That's what the difference is. So we're talking about a big, giant linear chromosome. It's going to come in, going to find a mistake. So an exonuclease in that case would have to start from one of the ends, and we don't want to do that. So it's going to cleave somewhere in the middle. It'll recognize what's incorrectly base paired. Cut that section out, and then you have the repair enzymes that can come in and now start from that 3' hydroxyl group and actually fill that gap in, and have a DNA ligase will come in and fill it in. So you go at the very end and you recheck all the work again. That's strand-directed mismatch repair. Now, a defect in that type of mismatch repair is responsible for hereditary non-polyposis colorectal cancer, HNPCC. Also, I want you to write this down because I didn't write it here. It's in your objectives. It's written somewhere on the PowerPoint. This is also called Lynch syndrome, L-Y-N-C-H, okay, Lynch syndrome. And you'll see those two names, HNPCC and Lynch syndrome, used interchangeably. They mean the same exact thing, okay? But the common name you'll frequently encounter as well, okay? So Lynch syndrome, I want you to know Lynch syndrome is a defect in mismatch repair. So it's a defect in correcting the work after DNA replication is done. So if you have a defect in a type of mismatch repair, what does that mean is going to happen? You're going to accumulate mutations, right? You guys know what happens when you start accumulating mutations? There's kind of a hint right there. You start accumulating mutations, inevitably you're going to get some kind of cancer. Anything that induces mutations ends up causing some type of cancer, okay? In this case, there's some specific proteins. I didn't give you the specific mismatch repair proteins that are defective in Lynch syndrome, but there's some particular ones, and they cause a particular type of cancer. This is a disease we're going to visit again in genetics. Okay? Okay, so that's how we deal with mistakes done during DNA replication. You also have other places where you can have mutations, where the DNA can be altered after replication. Okay, these are some types of spontaneous mutations. You can have exposure to certain chemicals, and one example I've given you here is this benzoate purine in cigarette smoke. And there's other things in cigarette smoke that can cause mutations. Not just cigarette smoke. Cigarette smoke happens to be the nastiest one, but any smoke is going to contain some types of carcinogens that cause mutations. Exposure to radiation can also mutate nucleic acids. Another example is exposure to UV light. Okay, and so those of you who like to spend a lot of time in the sun, including me when I play golf, you get exposed to UV light. UV light causes the formation of pyrimidine dimers, usually thymine dimers. So you would know from the last lecture, pyrimidines are C, U, and T, right? Cut the pie. So usually thymine dimers, and I've given you a picture there. You don't have to, I'm not going to ask you to draw it out, but you should know UV light can cause thymine dimers. That's particularly what you see. So you have enzymes that can come in and deal with these types of damage. In this case, with UV light, we have a specific set of enzymes called UV-specific endonuclease. It's actually more than one enzyme. It's a group of enzymes, but I wrote it as if it was one enzyme. Also called excision endonuclease or exonuclease. Don't confuse exonuclease with exonuclease. They sound kind of similar. All three of these are the same thing, just different names. Unfortunately, all three are used. Okay, so, and what this does is it recognizes damage, in particular caused by UV light, these thymine dimers, and it's actually going to come in, cleave on both sides of that, so it's an endonuclease, right? It's going to cut out where that section is, and then you can have your DNA repair enzymes come in and fill in that gap, and then you have a DNA ligase that come in and seal the nick. Okay. Pol I is shown in this, so we're talking about in prokaryotes, but you have this enzyme, a eukaryotic, a specific version of this enzyme as well. Okay, and actually a defect in excision endonucleases, or excision endonucleases, a group of them, causes a condition called xeroderma pigmentosum, and that's what's shown in this figure. So once again, so we're talking about DNA damage here. It causes mutations. What happens if you get mutations? I just said, what does it cause? Cancer, right? You end up with some types of cancer. So, and this kind of gives you an idea of how much your DNA is getting mutated. Okay, so people with xeroderma pigmentosum can't repair these thymine dimers, so they have to avoid UV light. And they're very, very, as you can see, prone to these skin tumors, which will eventually result in cancers, which will eventually kill them. But, so this would happen to you too if you couldn't avoid thymine, if you weren't able to repair it. So that kind of gives you an idea. And people with xeroderma pigmentosum actually try to avoid sunlight as much as possible. But you still always get some exposure, even from lights inside a little bit. And so it kind of gives you an idea of how much you're actually getting exposed to. So if you like to spend a lot of time out in the sun, you're really working your excision endonuclease. So, you know, one of the objectives that I gave you is to compare and contrast these two diseases, xeroderma pigmentosum and Lynch syndrome. You know, they have three different symptoms. They're both caused by defects in DNA repair, but different types of DNA repair. One, we're checking replication errors. In this case, we're actually, this is a post-replication mutation that happened because of UV light. And I think that's it for today. So I'm going to see you guys bright and early tomorrow, 8 o'clock. I'll go try to be awake. That's pretty early for me, but so I'll see you then. Yes.
On slide 22.